Welcome, my friends! Today we will be discussing the uniform distribution. In a uniform distribution, all values of the distribution are equally likely. For example, the number of minutes until the next bus arrives might range from 0 to 10 minutes. If all possible waiting times between 0 and 10 minutes are equally likely, the wait time would be said to follow a uniform distribution. The more common form of the uniform distribution is the continuous version. There is also a discrete uniform distribution, which we will not be discussing in this video. As the distribution is continuous, that means it can take on any value within some range. In our example, any time between 0 and 10 minutes. When I say any time between 0 and 10 minutes is possible, I mean any time between 0 and 10 minutes. This includes repeating decimals like 3.3333 repeating forever, or 1.91462 minutes, or any other possible value between 0 and 10. You can start to see why there are actually an infinite number of possible outcomes in any continuous distribution. This fact of continuous distributions creates a few interesting observations for calculating probabilities. As there are an infinite number of outcomes, the probability at any individual point on a continuous distribution is 0. So the probability of waiting exactly 3 minutes for the bus would be 0. It only makes sense to talk about ranges, such as less than or greater than 3 minutes, or perhaps between 3 and 5 minutes. Also, there is now no difference between greater than or equal to signs and less than or equal to signs in probability statements. Since there is no probability at a single point, the probability x is greater than some value, let's say 3, is the same as the probability x is greater than or equal to 3. For any uniform distribution, we must define the lower and upper bounds of the distribution. We let a represent the lower bound and b represent the upper bound. The notation x tilde u parentheses a comma b is read x follows a uniform distribution from a to b. If x follows a uniform distribution from 2 to 6, here is the notation that we would use. This would mean that every value in the distribution between 2 and 6 is equally likely to be observed. The graph of a uniform distribution looks like a rectangle that starts at a, or 2 in our example, and ends at b, or 6. The height of the rectangle is 1 divided by b minus a, which is 1 divided by 6 minus 2, or 1 divided by 4 in our example. For continuous distributions like the uniform distribution, the area under the distribution on a graph represents probability. The total area under a continuous distribution must equal 1, which represents 100% of the probability. You may remember that the area of a rectangle is simply the base times the height. Here, the base is 6 minus 2, which is equal to 4, and the height is 1/4. The area of this rectangle is the base times height, or 4 times 1/4, which is equal to 1. This verifies that the distribution is valid. We can also find probabilities by finding the area of different slices of the distribution, which we will do shortly. The mean of a uniform distribution is simply a plus b divided by 2. Remember that a equals 2 and b equals 6 in our example distribution. So we have 2 plus 6 divided by 2, or 8 divided by 2, which is equal to 4. The mean should fall in the middle of the rectangle if you have graphed the distribution. The standard deviation of a uniform distribution is the square root of b minus a squared divided by 12. We have the square root of 6 minus 2 squared divided by 12, which simplifies to about 1.15. Let's look at an example of calculating probabilities from a uniform distribution. Let's assume the age of students at a summer camp is uniformly distributed between 6 and 14 years old. Our random variable x is the age of a child at the summer camp in years. We say that x is uniformly distributed from 6 to 14 using this notation. The graph of the distribution is, you guessed it, a rectangle. The rectangle starts at 6 and ends at 14. The height of the rectangle is 1 divided by 14 minus 6, which is 1 divided by 8. We can verify that the area of this rectangle is 1, as the base is 14 minus 6, which equals 8, and the height is 1/8. 8 times 1/8 is 1. Let's look at some questions related to probability. What is the probability that a randomly selected child is exactly 12 years old? The answer is 0. Remember, for continuous distributions, there are an infinite number of points, so the probability of any exact point is equal to 0. What is the probability of a randomly selected child being more than 12 years old? This could be written as either the probability that x is greater than 12 or the probability that x is greater than or equal to 12. It doesn't matter which one we use, since the equals part doesn't add anything to the probability, since there's no probability at an individual point. The way we find this is by locating the corresponding area on the graph and calculating that area. Here is the area that's greater than 12. The base is 14 minus 12, which is equal to 2. The height is 1/8. Therefore, the probability is the base times height, or 2 times 1/8, which is 0.25. There is a 25% chance of a randomly selected child being more than 12 years old. What about the probability that a child is between 7 and 10 years old? We write this as the probability 7 is less than x is less than 10. You could also use the less than or equal to signs if you wanted to, but it makes no difference. Here is the area. The base is 10 minus 7, which is equal to 3, and the height is 1/8. The area is base times height, or 3 times 1/8, which is equal to 3/8, or 0.375. The probability that a randomly selected child is between 7 and 10 years old is 37.5%. All right, my friends, we have finished our discussion of uniform distributions. We will be exploring many more fun and exciting statistical topics that you won't want to miss, so make sure to check out our other videos.